everyone, I'm Horace, and me and Francis, we're going to share this zkMNIST app. All right. To set the stage a bit, why are we interested in machine learning and zero-knowledge proofs? So from some of the past talks and demos, we know that with zero-knowledge proofs, we can take private data, perform some computation on it, and then generate a proof of or a certificate of the result, right? And that's really useful for machine learning applications where we often have things that we want to keep private, right? So we might have like some sensitive data like biometrics that we don't want to reveal, or maybe we have like a machine learning model that we want to keep private because it's like intellectual property, right? So some applications, yeah, we might have a private model but public data, or a public model and private data, or public model and public data, right? So in the case of like a private model and public data, an example of this is, let's say we have this tumor classification model that we want to keep private, but we want to like just like certify that this model is actually really good. It classifies like 99% of images correctly on this public NHS public tumor data set, right? Or if we have some public model and private data, suppose, let's say, some insurance company or some financial company, they have a public credit score model, and you don't want to release your like financial information, but you want to like certify that, oh, I actually do have the assets to qualify for this big loan, right? And then finally, in the case of like a public model and public data, there's no sensitive information, but it's still like useful to verify the correctness of the results of applying this machine learning model on this public data, right? Okay, so as is tradition in the machine learning community, we always do proof of concepts on MNIST, which is this handwritten data set. So I'm gonna open up this app. Okay, so in this demo, we have a public machine learning model, and here we're like picking digits to use as our like private data set, and we're just gonna classify them. Okay. So this will take like, I don't know, a few seconds. So we picked 8, 2, 1, 3, and 6, and it's almost right. All right. Let's see, and now Francis is going to talk a bit about the model end.
Right. Thanks, Horace. I'm Francis. So want to give you a bit more kind of under the hood what's going on. So in case you're from the crypto community not familiar with machine learning, basically the example we gave here is a kind of very simple what's called a CNN, convolutional network. And it's basically a series of, as you see here, series of modules. Each module is very simple. It's basically some kind of matrix multiply, so it's times and add, basically repeated many times. And then there's some kind of a nonlinear function, and that's essential. So you just stack them on each other, and that's a very kind of plain vanilla neural network. And most neural nets are basically variants on this. So the point is that this is fairly easy to put into a SNARK because the the circom circuitry to arithmetize this, all that works. The hard part is probably the nonlinear part, which we'll talk about in a second. But here we put I think it looks like 7 or so layer network into the model. But we wanted to be sort of make sure it worked in our very limited time to do this project. So we picked the simplest possible thing, which was we put only the final layer here into the SNARK. So what we actually did was we executed the prior layer in a normal web app, JS, whatever. And then we put the final part, which is a set of matrix multiply, in this case a fully connected network, and then the softmax, which is the nonlinear decision kind of thing, into the prover of the SNARK. And yeah, so, and I guess I'm not sure where that goes, but this is actually instantiated via some matrix multiply, and then a argmax in the SNARK circuit. You can see that if you go to our repo of how we did that. And there are a number of challenges really more like things we had to learn, not so much challenges in every case going forward. So first one was we figured out that negative numbers don't kind of work that well inside the field inside the SNARK. So we want to make sure that everything was biased, so it's going to be positive. Second thing is that there's no floating points inside the SNARK circuit, so we have to think about how to quantize or how to make floating point models into integers. And this can be tricky because you don't want to overflow, so just kind of try it out and make it work out. The third part is really both a learning point as well as ongoing challenge, which is nonlinear activation functions are tricky to do inside a circuit. You can make it blow up basically if you have many layers of cascading functions like that. So that's why we picked only one layer inside our model. And there's many ideas for how to do that. For example, like x squared, x cubed, or different combinations of that. All this can be tried out, I think. And we've heard that there are people who have put impressively huge amounts of calculations into a ML model in the SNARK. So I think all that will be coming, especially as hardware acceleration becomes more common, which I think it will at some point. And the last thing is that this is more personal, speaking for myself. I had no clue what to do here, so I had to learn the whole tool chain for the zkSNARK, the dApp development. So the fact that we did it, this is the point. Please go to our repo and see what you can copy and paste from that. So then maybe the most interesting part for me was kind of the use cases here, right? So I won't dwell too much about the on-chain use cases. You can have, like we heard today, different DeFi or DAO governance voting kind of use cases, because all those cases where you want to do some kind of validation or checking, often machine learning is the preferred way to do that when the input data is not like completely crisp. You want to have some kind of, black box nonlinear function to go map from the input to some classified output. So whenever that happens, you may want to have a machine learning network in somewhere in the thing. Again, this is just a primitive. This is not meant to be a standalone, but this is probably a very powerful primitive to be cascaded together. But the off-chain use cases, as Brian said before, there's many things which are probably beyond blockchain. So I'll just touch on a few. So biometrics, right? Fingerprint analysis, where you have some kind of identity based on fuzzy real-world analog data. It could be your face, your fingerprint. It could be your gait as you're walking, the way you walk. So all these things are being captured by machine learning. IoT, so just automated sensors in our world. For example, cameras to monitor elderly people falling. Many cases you don't want the actual raw data to be exposed, but in many cases you want to actually have guaranteed, secure guarantees that these are actually being authentically supplied to the system. Location is interesting because there's of course GPS as a waypoint, but what's more interesting is like a combination, some movement via some pattern, or it could be being in a certain location near some specific waypoint. So all these things are no longer if-then statement. It's something more complicated that might require some ML model. Wellness, I sort of touched on, which is if I want to make sure that you're being rewarded, if you're walking or running or biking, whatever, all these things are actually pretty easy now to use accelerometers to kind of classify. But again, it could be an input into a more complicated use case. And Horace mentioned medical data, very private DNA data, or other kind of things. Future directions clearly can be deeper, bigger, better models, more computer vision, video analytics, maybe language models at some point. It could be other kinds of non-deep neural network models. And then there could be many, many applications we can't even think of right now. And I think that's it. Thank you.